Okay, so I want to talk about Verilog in this class, but before we talk about Verilog, I want to give you guys some perspective, right? So we have talked about transistors, right? We have talked about CMOS logic, and also in this class, we are doing gate level design, right? We have been doing gate level design, right, for the first few lectures up to this point. If you think about this transistor, actually, this is the physical layout, right? Even for inverter or NOR gate, right, or even SR latch, we already need to build up, right? We already need to use quite a few transistors, right? You think about today's chip, right? So we are dealing with so many transistors. It's probably not a good idea to design, right, at this level, right, at this very low level. But in the past, right, in the back good old days, right? So people are indeed, right, actually drawing out chip layouts by just using connecting transistors. Okay, you can imagine that this is probably not a very scalable process, right? Actually, even at the gate level, right? I hope that you guys have start to appreciate the complexity of chip design, right? You think about lab 1, even for a simple design like that, right? So that's basically a simple LED, right? This LED circuit. So where you guys just need to build up maybe 10-ish or 20-ish gates, right? But the challenge there is you have to minimize, right, the logic and then map it to the actual physical gates, and then you have to connect them, right? So that's also a non-trivial process. So think about today's billion transistor chips, right? This is definitely not sustainable, right? This is not a good idea. So that's why many years ago, easily 20 years ago, so the industry has already moved away from doing chip design and the transistor level and gate level, right? Because they are just not scalable, right? So the industry has started to build more abstraction, right? More abstract models. So one of the mainstream abstraction that people are using these days to develop, right, digital circuit is HDL, or Harvard Distributed Language. Right? So we're going to be learning Verilog. And this Verilog or VHDL, so HDL language like this, we can easily handle up to a few or maybe hundreds of million gates design without too much of issue. We basically let the CAD tools like quotas, right? So we write design at a higher level programming language, and we let the CAD tool to automatically generate a gate level circuit. And that gate level circuit will be lower to transistor level. So that's all done automatically by the computer. Or CAD, right? CAD means computer aided design. And for today's chip, right? So actually people, the industry and also academia, we are actually working on the next level abstraction. It's also part of the research, that my group is doing, right? So we're actually looking at what is the next level, right? So even HDL is actually too low level for complex designs these days. So what's the next level? Right. So this is actually not this is outside the scope of this class, this lecture. There's a question about Alma's asking if it automatically resets to 0 once it passes to yes, right? How many right? So basically, in some cases, right, especially when this factor, you are doing this divide by certain factor counter, right? So the factor is power 2, you can easily build it, right, by using this kind of a free running counter. Right? But in some cases, you may want to use another, right? Not 8, right? You may want to use 9 or 10. Then the counter logic will be more complex. All right. So coming back to Verilog or HDL. So like I mentioned, right, so this really enables us to build much more complex designs. So this is not something that if you keep doing the transistor level, if you keep doing the manual routing, right, manual wiring of those gates, that's just too time consuming, that's too error prone. And like I mentioned in one of the classes, you're actually not going to be building a more efficient circuit than the computer. So the computer will be running all sorts of algorithms to optimize and minimize the multi-level logic. Okay, not the 2-level, not using kernel map. And the languages that we're going to be using is Verilog. Okay, you guys are starting to learn it from lab 2. in the textbook, I believe it uses system Verilog, right? Which is actually sort of the successor to Verilog. It's gaining a lot of adoption already, but the good thing about Verilog is still, I believe, at this point, the most widely used HDL, at least in the US. And also, the moment you master Verilog, you'll be able to quickly understand what's going on in system Verilog. So this is why we are choosing Verilog. There's also something called VHDL. That one's more popular in Europe. That was a few years ago. Okay. So Verilog is basic language for hardware design. It's invented in 1980s, right, by a startup called Gateway, and it's later acquired by Cadence. Cadence right now is one of the major CAD tool vendors. Okay. One important thing about this kind of design languages is it actually supports modeling, simulation, and synthesis. Okay, it supports all these important tasks. I know that some of you might have taken some other digital logic design class where you basically just use some simulator, right? Basically model your design. You can draw these gate level schematics, right? And you can run it, right? So using some kind of simulator. But usually those tools are very simple. They do not offer this so-called synthesis capability. So what synthesis or what a synthesizer does is it basically converts your design, right? In this case, in Verilog, automatically and lower that to gate level abstraction and optimize it, and try to optimize it to optimize to optimize the performance, also the area, right, and cost and such, and power. And the tool that we are using, Cordis, actually does all three. Okay, so this is why we are using Cordis, because we actually want you guys to be able to program a real FPGA, okay, to be able to run a real circuit, right, not just something that's being simulated. And if you look at Verilog, so another important thing, you may actually find that it's sort of similar to C in terms of syntax in many cases, but really it's not a software programming language. It's a hardware programming language, hardware design language, in the sense that, so we actually care about structure a lot. It's highly structural. I'm going to explain what this means. And it's inherently concurrent. So it's really modeling the concurrent hardware, right? Things are running concurrently in parallel. And also, we have bit level behavior. So instead of just modeling 8-bit, 16-bit, 32-bit, and native types, so we can build a circuit with arbitrary bits. All right, so these are the sort of dry stuff, right? Very abstract. These are some of the key features of Verilog. I'm going to show you some examples pretty soon. Okay, so first, let's talk about some of the basic concepts, right? So in Verilog, you have to be able to specify binary values first, right? So in Verilog, each signal can actually take 4 values, interestingly, okay? Not just 0, 1. You can also write down X, okay? In our case, okay, in this lecture, also in this class, let's just treat it as don't care, okay? Or something unknown. Actually, X can represent either 0, 1, Z. Z here is not something that we'll run into very often in this class. It means high impedance. This really means that when your signal is not connected, it's floating around. It's not connected to 0 or 1. That's why we call it Z. It's a high impedance. Again, this is not something that's too important, right? In most cases, when you debug your circuit, you'll see these 3. Okay, 0, 1, X. In many cases, when you see X, is where you either forget to reset part of the circuit, or you intentionally do not want to reset based on the circuit. That's where the initial condition of your flip-flop or certain signal is basically unknown, right? Okay, so that's where we are seeing X. You will see X in the waveform in some cases. But again, in most cases, you will see just 0, 1, right? So these are the 4 values that Verilog can represent. And this is a modeling language, right? So we also have this so-called vectors or bit vectors. So this is where we can represent multi-bit values. So this is the way we represent a multi-bit vector. So this is the notation. So we use square bracket. right? So to specify the indices of this LSB, right? LSB is usually just 0, right? And MSB, right? This is how we specify a 8-bit vector in this case, right? From 0 to 7. And actually, so for Verilog, right? So the rightmost bits, right? So this is also our convention in this class. The rightmost bits is always the LSB, this significant bit. So this is our convention, it's our assumption, right? So this is a signal. We can specify variable. We can also specify constant. I think there are already some questions on Piazza about this constant, and also there's a typo, right, in the lab, I think in the tutorial, when we specify constant. So make sure you read the Piazza announcement. So we just corrected that typo in the tutorial. And this is how we specify constant. This is a binary value. Okay, so we use, first we specify the bit width. So it's how wide is this constant? How many bits do we have? Right, and then we use a quotation mark or basically single quote, right? Apostrophe to specify, okay, to sort of delineate, right? So the bit width from the rest. After the quotation mark, we need to specify the base. So what exactly is the base of this constant? When we have a B, right? So over here we have B. This means binary. So we also have D means decimal. Later on, we'll see H, hexadecimal in this class. We also have base being 8, right? Then we have O over here. Okay, so this is a base of 4-bit, right? Constant 1001, and this is the LSB, right? We can also do 8 bits, of course, right? So this is how we do it. We can even use X, right? We can use X in the constant. Then we have don't cares. Right, so these are binary values for decimal constant. So this is how we do it. Okay, again, see here, we can specify the bit width. Now you guys can even go to, right? So in some cases, we can go to 1000 bit, right? Without any problem. So Verilog actually allows this kind of specification. Your software programming language like Java, C, Python do not directly support it in the native types. Okay, so these big vectors, and here are some operators, right? Again, they are very similar to the C language, right? Just make a note, right? So this is how we specify the NOT gate, right? Ampersand, right? Caret for XOR, and vertical bar for OR, right? So these are the things that we use most often, right? Later on, we might use some of the other arithmetic operators, but not initially, okay? Not in the first few labs. I'm not going to elaborate much on this, right? This is very straightforward. Okay, so let me also talk about the structure, right, of the Verilog program. So usually we have a collection of so-called modules in Verilog. Right? Each module contains some declaration and some statements, right? Just like a software programming language. But in this case, actually, each module actually corresponds to some piece of hardware, right? When we actually generate the circuit. So what exactly is in the module? So here's an example. So we have, right, in this case, we have a simple module, and we have a module name here, right? Specify signals, right? So these are the input and outputs. So we put that in the parentheses, and we specify the inputs, right? This is output. In this case, we have 2 input, or actually 3 input, right? 1 output, 1 bit output, and these are some of the internal signals, right? So later on, we'll see use either wire or reg to specify internal signals. We can also use reg for output, and in some cases, right? So in some cases, but in most cases, we'll just use reg, right? So as internal signal. Okay, and we have some statements, right, which specify what exactly do we want to compute. All right. And that's just one module, right? So we can actually have many modules. each module can instantiate many other modules, and we have this hierarchy. Okay, later on we are going to be using this, right? But this is not like a call graph in software program. It's not like one module calls the other module. It's really like when we have this kind of arrows, it means that one module is instantiated inside the module. So there will be actual piece of a physical hardware, okay, when we generate circuits. All right, so again, these are the dry stuff. I'm going to show you some demo soon. Also, one more thing, we have something called this structural programming style and behavioral programming style. Right? So when we have structural programming style in Verilog, it means that we are explicitly instantiation modules. Okay, we are doing this module instantiation explicitly. It's just like drawing the circuit diagram using Verilog, right? So that's a structural mode. It's a behavior mode. That's where the code will look more readable, right, at a higher level. And that's where we use something called always block and assign. Right? This is something that we are going to introduce pretty soon. Right? So before that, let me show you guys some code. To go to another screen. All right, are you guys seeing the screen? This window, EDA Playground. Okay, good. All right, so I'm not running callers here. This is a website where you guys can quickly type up some code, and in this case, they support Verilog, I believe System Verilog and VHDL. The website EDA Playground. I'm not sure if you can see this or not. Okay, and they also support different kinds of simulators. Over here, I just entered the code that I showed you. Right? So this is actually a code specified in the structural style. Right? So again, by structural, I mean that we are explicitly instantiating some of the sub-modules. Actually, N here is a sub-module, or here is also a sub-module, okay, being instantiated inside this module. In this case, there's a top-level module called M21. And we also specify the connection, right, explicitly. See here, TX. So this is a wire. This is actually intermediate signal. And this wire, right, is connecting the end, right, and the OR gate here. Right, see here, there's another TX. So TX is output here, and here the TX is the input. That's how we draw the connections. Okay, so let's try to simulate this design. I actually also wrote up a test bench over here. You guys don't need to worry too much about this. Right, so that's where I apply some input stimuli to drive this this module to simulate. Let's see how I run this. Okay, so here's the waveform. Right. See here, this is actually a combinational circuit, right? This is conventional logic. Output, this is a waveform for out, right? Output directly right, respond to the input changes. We have 3 inputs, X, Y, and SEL, right? So when SEL is 0, output is the same with X. Right here, when SEL is 0 over here, so output reflects X. So when SEL is 1, right, raised to 1, right, output is the same with Y. Right. So this is a waveform. What exactly is the circuit doing? Any guess? What is the circuit? So I'm looking at the chat window. There are some questions about the syntax, right? Yeah, I'm going to talk about syntax a little bit more. But if you just look at the waveform, any guess? What is the circuit? Right, very good. It's basic mux, right? So we are basically implementing a mux, right, using this Verilog code, right? Over here we have 2 AND, right, and NOR. So this one, right, the tilde is doing inversion. Okay, so that we don't have to instantiate another NOT, right? So just for the sake of simplicity, this is structural form, right? And let's see, I can also show you another form. This is the behavior form. So where we are using this so-called continuous assignment. Right, again, same module, right? 2 input mux to the 1, right? To the 1 mux, right? 3 input, 1 output, right? So see here, so the difference is we are not explicitly instantiating those OR gate, right, and AND gate anymore. So instead, we are using this ternary select statement, right? It basically says that when select, right? So it's 0, so it's inverted, right? Tilde means inversion. So when select 0, we select X, right? Otherwise, we select Y. And we assign, right? So we directly assign the output of this expression to this out signal using this keyword. This is for continuous assignment. And this we can only use this keyword for composing combinational logic. Okay. All right, so this is a quick demo. Let's see whether I can come back to my screen. All right. Okay, so let's come back here. I think there's some question about, right? Somehow my, okay, all right, so my point is working now. I just showed you the structural style, right? Behavior style. And in most cases, we usually mix this two. Then we write the Verilog program. Of course, we want to stick to the behavior style as much as we can, right? Because it's simpler. Let's come back to this example, right? I think there are some questions about the syntax, right? On the chat window. So, right. Okay. Right. Let's explain the syntax. Right. What exactly N0, N1, and 0 or 0, right? What are these? This is basically N0, right? This is N1, and this is or 0. It's basically the name of this module, right? So we basically instantiate the module to a capital N, right? So the instance name is N0. We can instantiate again and then call the instance, right? So now we have 2 instances of N. The second instance is called N1. Does it make sense? All right. Any other questions about this? So I think I missed some of those when I'm running a demo. Does it refer to AND or OR gate? Yeah, I think most of the questions are related to this one, right? All right, is it clear? What exactly are we doing here with the module instantiation? Give me some response, guys. If it's still not clear, then just ask again. Cool. All right. Okay, so this is structural style, right? And this is something that I just showed you, right? So when we describe a simple circuit, right, like this, I recommend you guys to use assign, right? It's called continuous assignment, but this is only useful for specifying combinational logic, and also only useful when you have a short expression like this, okay, like a mux. And you may have many assign, right? You can actually do many other assign, right? Like this, R1, blah, blah, and we can do R2, right? One important thing is that the order of this assignment does not matter at all. Because basically each assignment, right, specify a piece of logic, right, in hardware. So we don't really care about order, right? The R1 can go before out, R1 can go after out. In the end, we'll have 2 pieces of logic, combination logic in hardware, and they're running in parallel. They're running concurrently. It's not like these are evaluated in sequential way, right? So that's what I'm saying, right? So this multiple assignment, right, happen in parallel. So keep this in mind. So this is very different from writing a software program. So when you write out things like this, like Verilog, everything is either structural, right, or in things are in parallel, right? Everything's in parallel. Okay, so the order does not matter. And here's something very important. Okay. You'll see we use it so often, right? Always block. I think some of you are already using it, right? So for lab 2, okay, for always block, we can actually use it to specify either combinational logic or sequential logic. Okay, so this is actually where some confusion may come in. If you have time, I'll also ask you guys to do a quiz at the end, right, about this, right? So make sure that you pay attention, right? So with the always block, we write always, right? So this is a keyword, and then we specify this so-called sensitivity list using this. Basically, we say that always at, right? Always, in this case, always at, this at specifies sensitivity list, right? So the things inside always block, okay, they may or may not use the signal specified on the list. But why do we need this list? So it says that, so the semantic says that if any of the input, right, on this list changes value, so during simulation, right, during simulation, so the statements inside always block will be triggered, will be running, right? So basically statements inside always block will be sensitive to the changes, right, of the signal specified in this list. That's why it's called sensitivity list. So in this case, this is mux, right? It's fairly straightforward, right? So indeed, right, we are indeed sensitive, right, to all of these signals. So later on, we can actually specify wildcard, right? So we just say like star, right? So basically everything, right, all the inputs used in the statements, right, will be specified on the sensitive list. There's actually shorthand that we can use, right? Okay, so there's some question, right? It's great that you guys are already looking at the tutorial. So we have something called blocking assignment and non-blocking assignment, right? I'm going to talk about that, right? So Alma, you're right. So if there's only a single assignment in always block, it doesn't really matter. So in this case, we are using the so-called non-blocking assignment, right? It doesn't really matter much, right? Because there's a single statement. But I'm going to talk about this. Before that, here's the important thing. Okay. So for anything in the always block, okay, for anything that we write in the always block, like this, like out, we need to use reg. We need to add another keyword, right, to specify the signal. Reg is a shorthand for register, but like I mentioned earlier, right, so reg may not be translated by the CAD tool as a register. So depending on how you actually use it. But again, so it's really important that, right, so reg is always needed for Verilog. If you have a, right, so if this signal happens on the left-hand side, right, this is basically left-hand side, LHS, right? Is it written? Then we need a reg to quantify this variable. Okay, so there are some other questions. Right? Jacob is asking, right, do all variables have to change or only one for the always block? Very good question, right? So Luke is correct, right? So if any of this signal changes, this is the list, right? So if any of this signal changes, then the always block will be triggered. Right? Is it clear? Always? In this case, right? So in this case, we are using always block to specify a combination logic. Right? This is indeed a combination logic. All right, and we can also use always block to specify sequential logic. Again, pay attention, right? Because we might be doing a quiz at the end. Right? So over here, I have two pieces, right? Two always blocks. Okay? But I have to, okay, I have to be clear. So these are two separate programs, right? You actually don't want to write two always block in the same Verilog code. which write to the same output, right? The CAD tool will reject that. Right? These are two separate pieces of programs. Right, so let's first look at this. Right, so there's some more questions about the difference between wire and reg. Right, so we're going to get to that. So if you look at this piece of program, what is the first one? What exactly is the first one doing? It's something that we just learned. Can you guess? Very good, Emily. Right, it's a D latch because it's sensitive to clock, right? And this is level, right? This is level sensitive, right? When clock is high. So this if statement says if clock is high, you assign D to Q. Right? So this is a latch. Second one, it's a D what? Taylor, right? DFF. Right? The second one is edge triggered, right? See here. So we actually need to use this pause edge. This means positive edge. Means that we are responding to the positive edge of the clock, and that's where Q, okay, will be automatically inferred by the CAD tool as a DFF. Okay, so this is really important. Okay, when do we have conventional logic? When do we have flip-flop? When do we have latch? I think there are some other questions, right, about the difference between wire and reg. And yeah, so like I mentioned, I think Amanda is talking about this, right? So if you're writing, right, so the signal is being written in the always block, you always need to use a reg. You cannot use wire. Okay. So the thing is the reg can become wire in some cases if it's conventional logic, right? But for continuous assignment, you always use wire. This is kind of confusing, right? This is something that you guys will get used to. But again, for always block, right? So we have to use reg. We cannot use wire. And there's another question. So almost asking if you are doing structural style, can you instantiate two modules with always block or no? What do you mean by instantiate two modules using always block, Alma?
I just mean like if you instantiate two submodules that have inside of them an always block, is that okay? Or
Yes, right. Good question. Yes, that's fine. Right, you can use always block to describe one module, right, and then basically wrap it up, right? You encapsulate it, right, using the module, and then you can instantiate it in a higher level module. And this can be hierarchical. And you can do however levels you want, however number of levels you want. Okay. All right, so coming to this thing, right? Blocking assignment. Okay, this is one of the more confusing, right, concepts, blocking versus non-blocking. Right, with blocking assignment, we are using the equal sign. Okay, so the only matters actually, when we compare blocking and non-blocking, when we have multiple statements in always block. So with blocking assignment, it really means that the right-hand side, okay, gets evaluated in a sequential way. Right? So base assignment to the left-hand side also. Okay, basically, base statements, right? So statements get evaluated in a sequential way and assigned to the left-hand side, basically the output signals right away, immediately. So this is simulation behavior. Okay, again, so I have to distinguish. This is simulation behavior. So this is something that we can simulate. And this is a flip-flop, right? So since we have always block, where the sensitive list has right, this clock edge, right, as part of the list. This is both Y and Z. In this case, both Y and Z. Okay, they are becoming the real registers or real flip-flops. So with blocking assignment, what do you mean by sequential way? Like what do you mean by immediate? So really, if you look at, right, so these two statements, first we assign A and B to Y, right? So with blocking assignment, you can just imagine that Y already has the new value. Right? Y is already, right, overwritten by A and B. That's it. Right? Then after that, if you use Y again, you can just plug in A and B. That's it, right? This assignment to Y is immediate. This is what the blocking assignment means in the simulation behavior. And this is actually the resulting circuit. So, once you understand the simulation behavior, I hope that you guys can really master, or really appreciate what it's doing. So in the real hardware, after synthesis, right? So I say this post synthesis. Right, first we have two flip-flop, right? So Y is a flip-flop, right? This is real hardware, right? Then we have AND gate here, right? So this is AND gate. So the output of AND, right? So is connected, right, to the input of Y, right? This is right, not surprising, right? But really with blocking assignment, so this is something you guys need to know. When we do blocking assignment, basically we really want to directly connect, right? So over here we are using Y, right? So really we want to use the input side of Y. Okay, when we connect it to Z. This is really the input side of Y, right? Because the assignment is immediate. This may not be too clear, right? At this point, I'm going to come back to this maybe in the next lecture. But for now, so make sure that first you can distinguish, right? So there's one way to interpret it, which is the simulator's way, or you also want to know, right, how to actually draw the actual circuit. Okay, when I ask you to look at the piece of Verilog code, and this is the actual circuit, right? So this is basically where we use the input side of Y. Y is a flip-flop, right? We use a D input, and then we connect that to the input side of Z. Then we assign Y to Z, right? In this case, we are assigning inverted Y to Z. Okay, so this is blocking, right? So basically everything, but the simulation behavior is probably more natural, right? It's probably not more intuitive, right? Everything just happened, assignment happened right away. With non-blocking assignment, we are using less equal, right? Or like an arrow, right? So this is the way to specify non-blocking assignment. So this is where, in the simulation behavior, we basically treat all the assignment, all this evaluation, all this, the computer, the statements as running in parallel. And assignment to the left-hand side, to the output signals, are not immediate. So they're sort of delayed until the end of the always block. That's the simulation behavior for non-blocking assignment. Okay. And here's the interpretation, right? So one way to look at this is, for non-blocking assignment, one way to think about this is you can just, instead of reading the statement, right, from top to bottom, you actually reverse this. Okay, so that's actually one way to interpret. Okay, so this way, things you'll be correct. Okay, basically when we assign to Z, we actually use OY because we delayed assignment to Y, right, at the end of the always block. Right, so that's the difference. So the assignment is not immediate. So this is where Z does not get the latest Y. And of course, Y is still A and B. And this is the resulting circuit. So see the difference here? I really want you guys to compare. Okay, I'm going to go back. Okay, so see here, right? This is the blocking assignment, right? The input is coming from, right, the input side of Y. You go back to non-blocking assignment. Really, when we assign to, right, when we connect to Z over here, we are using the output side of Y. This is delay, right? We talk about, basically we can treat a register or flip-flop as a delay element. Right? It's like a one-cycle delay. Okay. I'm going to make it even more clear the next time, right? But these are the things that you guys can try to remember first, right? And you will start appreciating hopefully soon, right? About why do we need a blocking assignment and non-blocking assignment? Really, it's really about this help us to construct different kinds of circuits. Okay, so how can it be one cycle delay if the clock isn't inverted? We're talking about the clock here, Alma?
Oh, actually, never mind. I just got confused. It's fine.
Okay, Oh, actually, the clock is always there. So I'm just assuming that there's a clock signal. All right, so these are not something that easy to understand at first, right? But I just want to let you guys know the rules first, right? So the definition. So we'll try to make sense of it a little bit more next time.